So good morning, students. Welcome you all for this session. So I'm going to today I'm going to start with the subject name is digital communication, bearing the code of 18HC61. Today I'm going to start with the module 1, that is band pass equivalent to low pass. So under this, first I start with the Hilbert transform. So far what you learnt using the Fourier transform, that is comes under frequency selective filters. So what frequency selective filter gives is, it is going to give the exact what frequency signal is present and its power related to that signal. So whereas the other filter technique, which is going to use the phase as the parameter to filter the signal. So that concept only the Hilbert transform, which is offered plus or minus 90-degree phase shift. Okay, so since it is offering plus or minus 90-degree phase shift, it is also known as the quadrature filter. So when the phase angles of all the components of a given signals are shifted by plus or minus 90 degree, the resulting function is known as the Hilbert transform. Okay, and it is also known as a quadrature filter because it is going to shift plus or minus 90 degree. That's why the named as quadrature. What is the expression to represent Hilbert transform? That is the symbolic representation cap, which is going to indicating the Hilbert transformation of the signal. What is here is, so you are going to transmit the g of t. So g of t is the signal. You are going to transmit it to the filter, that is Hilbert transform is the filter. Okay, so that is going to be given to the output of the filter is g. The output of the filter is g cap of t. The output of the filter is g cap of t. Okay. So now what g of t you are feeding as an input, and you are extracting g cap of t of the field as the output with the help of the filter is known as the Hilbert transform. So what is the inverse of it? How you are going to get it as? So that is you are feeding, you are extracting, that is g cap of t, g cap of t you are feeding, that is g cap of t as the input to the inverse Hilbert transform as the filter, and the output is g of t, So now when you are going to transmit that signal through a g cap of t through a inverse Hilbert transform filter, you retrieve g of t. What is g of t? G of t is equal to minus 1 by pi integration minus infinity to plus infinity g cap of tau divided by t minus tau into d tau. Whereas what is Hilbert transform of the signal of g of t? That is g cap of t, so is equal to 1 by pi minus infinity to plus infinity g of tau divided by t minus tau into d tau. So this is about the expression regarding Hilbert transform and its inverse operation, that is inverse Hilbert transform. Next, what is the function of it? That is the time function in terms of Hilbert transform. It is represented as 1 by pi t. So this can be represented in terms of Fourier transform, that is 1 pi of 1 divided by pi t is equal to minus j signum of f. What is signum of f? Signum of f is going to have the magnitude as 1 when f is greater than 0, and it is going to have the magnitude as 0 when f is equal to 0, and it is going to have the magnitude of minus 1 when f is less than 0. Okay, so the Fourier transform of pi by t is minus j signum of f, and what is signum of f? Signum of f is equal to 1 0, 1 for f is greater than 0, 0 for f is equal to 0, minus 1 for f is less than 0. So this Hilbert transform can be represented in terms of time domain, that is g cap of t is equal to 1 by pi convolution of g of t. This can be represented using the Fourier transform. Instead of g of t, it becomes g cap of f. G cap of t becomes g cap of f is equal to Fourier transform in terms of 1 by pi t, that is minus signum of f, and into the Fourier transform of the g of t is equal to g of f. So this is going to be the Fourier transform of the signal g cap of t is equal to g cap of capital G cap of f. So now from the equation 3, the signal g of t which is Fourier transformable, we may obtain the Fourier transform of its Hilbert transform g cap of t by passing through g of t through a linear time invariant system whose frequency response is equal to minus j signum of f. So what do you mean by linear time invariant? So the linear components is not going to vary with the time. It is linear time invariant system whose frequency response is equal to minus signum of f. This is what is the block diagram representation of Hilbert transform. That is, you are feeding for the Fourier transform g of t, then that becomes g of f, and you are getting multiplied with the pi of t, the Fourier transform, as minus j signum of f, and it is the output is g cap of f. When you are going to transmit that one to a inverse Fourier transform, so you are going to get it as g cap of t. Okay. This is the spectrum of h of f, where it is going to maintain the magnitude of 1 for entire all the frequency, for the negative frequency as well as the positive frequency. Once you are going to drawing the spectrum, so then you are going to get the positive as well as negative frequency. Okay, so the first is depicting the magnitude, and this one is going to be related to the phase. So what is the phase shift it is going to offer? It is going to offer plus or minus 90 degree phase shift. Okay, that is plus 90 degree phase shift for negative frequencies, this is for minus f, and minus 90 degree phase shift for positive frequencies, because this is due to the spectrum. Okay, so that is what this system is considered as. It produces the phase shift of minus 90 degree for all positive frequencies in the input signal, and plus 90 degree for all the negative frequencies, as shown in the figure. So what is the amplitude of this filter? The amplitude of all the frequency components are unaffected by transmission through the device. Such an ideal system is referred as the Hilbert transformer or quadrature filter, because the amplitude, the magnitude is going to be constant throughout for all the frequency range. So because of that reason, the amplitude is going to be constant. Only it is going to vary the phase. So because of that reason, it is known as the Hilbert transform. So what are the properties of the Hilbert transform? The Hilbert transforms differs from the Fourier transform. It exclusively operates in time domain. It has its own properties which are listed below. What is the property of 1? The magnitude of g of f is equal to the magnitude of g cap of f in terms of Fourier transform. That is, why? Because it is going to have the magnitude constant throughout any of the frequency range. That is 1. So magnitude of the signal is not going to affect. The amplitude is going to be constant in case of Hilbert transform. So because of that reason, g cap of t is equal to minus j signum of f times the Fourier transform of g of t. So the magnitude of j signum of f is equal to 1 for all f. So we can get g of t and g cap of t have the same amplitude. Since I have told you already, this becomes constant. What is the property 2? So if g cap of t is the Hilbert transform of g of t, then Hilbert transform of g cap of t is minus g of t. So that is nothing but when you are going to transmit a cos function to when you are going to give the 90 degree phase shift, it becomes sine. When again you are going to take the signal of sine and give the 90 degree phase shift to that becomes the minus cos. So that is what it means. So that if g cap of t is the Hilbert transform of the g of t, then the Hilbert transform of g cap of t is minus g of t. So that is what here they are twice the Hilbert transform is equivalent to passing the g of t through the cascade of linear two-port devices. So overall the transfer function of the device is minus j signum of the whole square. So the value of this is going to always, it is going to have the value 1 for all f. So because of that reason g cap of t is equal to minus g of t. So the system has the input is x of t, the input here it is x of t, and given to the system which is having the minus 90-degree phase shift, and you are extracting the Hilbert transform of it. So what is this system is going to have? So this system is going to have the transfer function. So that is h of omega is equal to the, which is going to combination of magnitude and phase. What is the magnitude? The magnitude is h of omega and e to the power of j theta omega. What is this theta is going to vary? Theta is going to vary plus j by 2 for omega less than 0 minus j by 2 for omega greater than 0. So now what is this theta value? It is plus or minus pi by 2. When you are going to substitute here in this place, you are going to get the magnitude response that is h of omega is equal to e to the power of, in place of theta you have to substitute it as pi by 2. Here the first term becomes e to the power of, that is complex exponential, that is e to the power of plus j pi by 2. So that can be extended using the sine and the cos function as cos pi by 2 plus j sin pi by 2. We know that cos 90 degree is nothing but 0, cos sin 90 degree is nothing but 1. So the answer is, for this expression, the answer is j. Similarly, so e to the power of minus j pi by 2, that is cos minus pi by 2 plus j sin minus pi by 2. So here the answer minus pi by 2, since sin minus 90 degree is nothing but minus 1. So the answer is here is minus j. So when you are going to substitute that is h of omega is equal to j for omega less than 0 minus j for omega greater than 0. So when you take, when you substitute in place of j as 1 and take that omega j to the LHS of the equation, okay, so for omega is less than 0 and omega is greater than 0. So this can be, this function can be treated as a signum function, that is inverse signum function, that is 1 for omega is greater than 0 minus 1 for omega less than 0. So since we are getting the inverse operation of it, so we can take it as minus sin omega. We can consider it as minus sin omega, and h of omega is equal to, now the h of omega, now take the j to the right hand side, that is RHS. So now the h of omega is equal to minus j signum of omega. So what is the Hilbert transform of the signal x of t? That is x h of omega is equal to x of omega into h of omega. So now what is x of t? X of t is the Fourier transform of x of omega. X h of t is the Fourier transform of x h of omega. Now what is x h of omega? X h of omega is minus j x of omega into signum of omega. So what is in terms of time domain? It is x h of t, that is inverse Fourier transform of this function, that is minus j into x of omega into signum of omega. Now what is the time domain representation? The signum of omega, it is pi by t. So when you are going to substitute, that is h is nothing but the Hilbert transform. Suffix here it is denoting it as the Hilbert transform. That is x h of t is equal to 1 by pi x of t into 1 divided by that is the x of t convolved with 1 by t. So that now the equation becomes 1 by pi, the integration of minus infinity to plus infinity, x of tau divided by t minus tau into d tau. So what is that? X h of t is the Hilbert transform of x of t. X h of t is the Hilbert transform of x of t. This is how we get the signum function as pi by t. So actually signum of t is equal to 1 for t is greater than 0 minus 1 for t is less than 0. This is the magnitude of it, the phase shift, that is plus 1 for positive frequency, minus 1 for negative frequency. So actually the signum of t, this since it is a 1, it is considered as a unit step function which is satisfy the odd symmetry components, that is u of t is equal to minus u of minus t. Then u of t is equal to, the Fourier transform of this is going to be 1 by j omega plus del of omega into pi. This is the Fourier transform of unit step function. What is u of minus t? So u of minus t is the Fourier transform of it is 1 divided by j of minus omega. That is what, wherever t it is plus omega, wherever minus t it is minus omega in case of Fourier transform. So pi into del of minus omega. So now when you are going to add these two, you are going to get it as in the second equation, when you are going to take the negative as the outside, then it becomes minus 1 by j omega plus pi del of omega. So what is that del function? Del function is going to have the value 1, that is the impulse. So the Fourier transform of signum of t is equal to 1 by j omega plus del of pi minus the 1 divided by j plus del of omega j phi. When you are going to subtract it, you are going to retrieve the signum of t is equal to 2 divided by j omega. This del omega into pi and this minus del omega into pi is getting cancelled. Now only the signum of t is equal to 1 by 2 j omega. So this is what the Hilbert transform you are going to transfer in the system, that is x of t. It is transmitted through the system which is considered as a Hilbert transform, and the outcome is x cap of t. Now by applying the property of duality, that is x of t is equal to x of omega. So x of t, when you are going to retaining it as a time domain, that is capital X of t, that is equal to 2 pi into x of minus omega. Wherever t you can take it as minus omega. Wherever w you can, wherever w you are going to find, you can take it as t. Wherever w it is t. So that is what the modification here in this case. So by doing that modification, 2 by j omega is equal to sine of t. Wherever t, take it as minus omega. Wherever omega you are finding, take it as t. That is what substitution here in this case. Then after substituting, it becomes 2 divided by jt, that is minus 2 pi signum of omega. So now you interchange this j and t term here. So this j and pi term, pi to the towards LHS, towards LHS, and t toward j towards RHS. So after changing it, it becomes 1 by pi t. This is equal to, the Fourier transform of this is equal to minus signum of w, that is, so here 2 is getting cancelled. Okay, that becomes minus j signum of w. So this is what the relationship of pi by t in terms of Fourier transform. Okay. Next, so we come to the property 3, that is the Hilbert transform. What is that? That is integration of this g of t and g cap of t with respect to infinity is equal to 0. So that is what here you g of t, the time domain can be transferred g cap of t, that is Hilbert transform. G cap of t, again you are going to transform to the Hilbert transform, you are going to get it as minus g of t. So this is what in the frequency domain approach. So when you are going to integrate, that is minus infinity to plus infinity, g of t, in g of t we have written in frequency domain as g cap of f is equal to, that is g of t. What is g of t? So g of t can be written as g of f, and this Hilbert transform of this becomes, that is g minus of f. That is what here substitution, g cap of f into g of minus into df. So now next is in place of g cap of f, substitute what is the Hilbert transform of it, that is minus j signum of f into g of f, and g of minus f retain as it is. So take the j term the outside of this and retain the signum of f and g of f, and in place of g minus f, since it is satisfying the odd symmetry, I am writing it as g convolution of the g star of f into df. Okay, conjugate. So g of f and g conjugate of f into df. So what is this conjugation means? That is g conjugate of f is equal to g of minus f for real valued signal. So what is the g cap of t? The integration of g of t in g cap of t into dt is equal to minus j, take the outward, and the signum and g cap of the magnitude to the whole square. So this is going to be the odd function. That is what they specified here. That is the above right hand side of the above equation, integration of odd function, because the product of odd function signum of f and even function g of f square is getting cancelled. This is acting like odd symmetry, and this is going to be a even symmetry. That is what it is going to satisfy the even symmetry. So because that is g of f is equal to g of minus f. Okay, so that is even symmetry signal. So the integration of this odd and even symmetry function is going to be is equal to 0. Hence the theorem is got proved that minus infinity integration with respect to minus infinity to plus infinity, g cap of t into g of t into g cap of t into dt is equal to 0. So regarding the problem solution regarding the Hilbert transform, the x of t is the signal, should be transmitted through a filter. So what is the output we are going to get? What is the outcome of the filter? So cos 2 pi fct can be written as in terms of a complex exponential, that is 1 by 2 e to the power of j pi fct plus e to the power of minus j 2 pi fct. So that can be converted in terms of del function. You can take the Fourier transform, that is 1 by 2 del of f minus c plus del of f plus 3 f plus c. Okay, after taking the Fourier the Hilbert transform of it, that is minus j signum of f is getting multiplied with x of f. So in place of x of f you substitute this. So that is what done here. So is equal to minus j divided by 2. Take the constant term outside, that is 1 by 2 signum of f del of f minus fc plus del of f plus fc. For negative frequency, the value of signum function is going to have plus 1. Here it is plus 1. And for positive frequency, the value is going to have minus 1. So here it is minus 1. So now what is the value? That is when you are going to, again you are going to multiply it with the both the denominator and the numerator as j. So the answer becomes x cap of is equal to 1 divided by 2j del of f minus fc minus del of f plus fc. So that is equal to sin 2 pi fct. So this is the Fourier transform of sin 2 pi fct. Hence the Hilbert transform of cos 2 pi fct is sin 2 pi fct. Next, so when you come to the problem 2, so that is x of t is cos 2 pi ft plus sin 2 pi ft. That x of t is equal to e to the power of minus j 2 pi ft. So x of t is equal to cos 2 pi ft plus sin 2 pi ft, and you are making the plus or minus 90 degree phase shift. Okay, plus 90 degree phase shift, it becomes sin 2 pi ft, and here it becomes cos 2 pi ft. So when you take the complex exponential, so that is cos 2 pi ft, since here it is minus, it becomes, cos 2 pi ft minus j sin 2 pi ft, shifting the 90 degree. So cos becomes sin become minus cos, minus cos here. So when you are going to substitute multiplied with respect to the j here, so this becomes minus j e to the power of minus j 2 pi fct. Okay, so this is the problem 3. So where you are finding the Hilbert transform of sin 2 pi fct. So when you are going to write the complex exponential the sign, that is 1 by 2j e to the power of j 2 pi fct minus e to the power of minus j 2 pi fct. So after taking the Fourier transform of it becomes 1 by 2j del of f minus fc minus of del of f plus fc. So now after taking the Fourier transform of it, you substitute in place of x of f. Okay, after substituting the signum of f, that is f is equal to when del of f minus fc is equal to 1, when f minus fc, that is what del is going to be impulse, that is existence of the signal when f is equal to 0. So this is only the magnitude you are going to get in case of del function. It is an impulse function. F minus fc is equal to 0 and f is equal to fc. The signum function having plus 1. when del of f plus fc is equal to 1, when f plus fc is equal to 0 and f is equal to minus fc, and f is less than 0 and the sigma of f is equal to minus 1. So what is x of f? X of f is equal to minus 1 by 2 del of f minus fc plus del of f plus ft after substituting and making that into a complex exponential. This becomes minus cos 2 pi fct. This is what the example how to draw the magnitude spectrum for the Hilbert transform for the low pass. So which is going to have the minus w to plus w the frequency and having the magnitude g of 0. So when you are going to transform to the Hilbert transform, so since it is going to have negative frequency comes under the positive magnitude and the positive frequency comes under the fourth quadrant. So this is what the Hilbert transformation of the low pass signal. Okay, so I'm going to end up now. The next session I'm going to start with next video. Thank you for watching this.